Yes, students, today we discuss the second part of MOT. In first part, we discussed about comparative study of VBT and MOT. Then we talked how molecular orbitals are formed, what type of molecular orbitals are there, their formation. All these parameters were discussed in our first part. Now today we will be talking about types of molecular orbitals. How many types are there? Molecular orbitals are of two types: sigma molecular orbital and pi molecular orbital. Now, how sigma molecular orbitals are formed? First, we discuss about this sigma molecular. Children, I think you must be remembering the formation of sigma and pi bonds. How sigma bonds are formed? Can you tell me? Yes, I think it's absolutely clear to all of you that sigma bonds, they are formed head-on-head overlapping on internuclear axis. Same here, sigma molecular orbitals are formed. And these sigma molecular orbitals, they are formed by SS overlapping or by PP overlapping. Let us first discuss the overlapping in two S atomic orbitals. Yeah, who will tell me the shape of S atomic orbital? Yes, correct answer. It is spherical shaped atomic orbital. So let us take these two S atomic orbitals. Suppose this is 1s, so this also 1s. So when these two 1s atomic orbitals, they overlap, it can take place in two ways: either constructive interference or destructive interference. If it would be constructive interference, that is additive overlapping. So in this constructive interference, that is Xi1 plus Xi2, we will be getting bonding molecular orbital. So the representation of bonding molecular orbital, we will be representing it something like this. This is clear. So this bonding molecular orbital, which is formed on internuclear axis head-on overlapping, so we call it sigma 1s. This is bonding molecular orbital. Got it? So now the second one is formation of antibonding molecular orbital. So this is 1s, again 1s. So for anti-bonding, subtractive overlapping or destructive interference, that is Xi1 minus Xi2, this will give us anti-bonding molecular orbital. Representation of this somewhat like this. Sigma star 1s, anti-bonding molecular orbital. Now, one important aspect here, just look at this point. Between these two parts, electron density is 0. So the part of 0 electron density is termed as, what do we call it? Yes, nodal plane. We discussed in atomic structure unit now. Nodal plane is the space where probability of finding electron is 0. So this 0 electron probability part is termed as nodal plane. So we can say here we find only one nodal plane. So in this way, easily you can check how many nodal planes are present in a particular case. So got it? Formation of sigma bond with the help of s orbital. Similarly, you can show in case of 2s, absolutely in same way. Now we discuss formation of sigma bond with the help of p overlapping. That how p orbitals will make sigma bond. Now children, for this, first tell me the shape of p orbital. Yes, what's the answer? Yeah, of course, it's dumbbell shaped orbital. But in p again, there are three degenerate orbitals. These are px, Py and Pz. Just take the example of nitrogen molecule. Formed by nitrogen, atomic number of nitrogen 7, electronic configuration 1s2, 2s2, 2p3. And in 2p3, the electrons are distributed as 2px1, 2py1 and 2pz1. One electron in each orbital. Now, in nitrogen, we know a triple bond is present. In triple bond, one bond in sigma and the remaining two are pi bonds. Now the question comes to our mind that out of these three, which one will make sigma bond and which one will make pi bond? The answer is absolutely simple without any confusion. You can say as these three are degenerate orbitals, it means anyone can make sigma bond. It can be px, it can be py, it can be pz. But there is a convention in chemistry. Most of the books they consider z axis as internuclear axis. So they say pz will make sigma. But the good books always says that it can be formed by any orbital because these three are degenerate orbitals. So as most of the books are considering pz as internuclear axis, so here also we will take in the same way to avoid any kind of confusion. So let us say that sigma bond is formed by pz, right? So pz as it is forming sigma bond means we take this on internuclear axis and shape of p orbital is dumbbell shaped orbital, right? This is first p orbital on internuclear axis. Now this is second one on internuclear axis. This is 2pz, 2pz. For sigma and for bonding them, it would be constructive interference. Similarly, Xi1 plus Xi2, all of you can easily tell. Now the resulting molecular orbital will be showing in this way. This is, that's it. And what do we call it? Sigma 2pz. Now, can you tell me where is the nodal plane? That is the place where probability of finding electron is 0. We can easily locate it. Yeah, it's situated. One is here and the other is here. So, how many nodal planes are there? 2 are there. Nodal plane 2 are there. So, this is representation of bonding molecular orbital. Now formation of anti-bonding molecular orbital. So this is bonding molecular orbital. Formation of anti-bonding. Now anti-bonding molecular orbital is formed by destructive interference, Xi1 minus Xi2. So, representation of these molecular orbitals. This is the way. Now, try to locate nodal planes. Very easily you can tell me. This is the one nodal plane, 0 probability region. This is the second 0 probability region. And this is the third 0 probability region. So, we can say here number of nodal planes is 3. And how do we represent it? Sigma star 2pz. That is anti-bonding molecular orbital. So, children, here we discussed how sigma bonds are formed by SS overlapping and by PP overlapping. After the formation of sigma bond, Now we talk about formation of pi bond, that how pi molecular orbitals are formed. The pi molecular orbitals, they are formed by pp overlapping. Pi molecular orbitals formed by pp overlapping. This can be px or it can be py. Px overlapping we can discuss, or py overlapping. And we know pi bond, it is formed by sidewise overlapping perpendicular to the internuclear axis. Got it now? So just take, this is first orbital, this one is the second. 2px, 2px. If it is constructive overlapping, that is xi1 plus xi2. Pi bond is formed above and below the internuclear axis. Remember? So this is representation of formation of, and we show it pi 2px. And nodal plane, this is clear, only one nodal plane. Zero probability region. Understood? Now we talk about formation of antibonding pi. First P, second P, 2px, 2px. These are the representations of wave functions, and of course destructive interference. I think now you people can easily represent all these things. Absolutely clear to you. And representation of the molecular orbitals, something like this. Nodal planes, these are the two nodal planes. Zero probability region. Yes children, all these things are clear. How sigma molecular orbitals are formed, how pi molecular orbitals are formed, their representations, what are the main conditions for their formation. So this was one part of MOT which we have completed right now. I think this part is absolutely clear to all of you. Now let us start with the another part, that is writing electronic configuration of molecular orbital, that how electrons are filled in molecular orbitals. Before this, in atomic structure, you discussed filling of electrons in atomic orbitals. And if I asked you, tell me the electronic configuration for carbon, atomic number 6, I think very easily you can tell me, ma'am, this is 1s2, 2s2, 2p2. Yes, na? So, 1s2, 2s2, 2p2, very simple. But we cannot write in this way for atomic molecular orbitals, because in molecular orbitals we will be having sigma molecular orbital, pi molecular orbital. So how do we write for that case? Before starting that, first you need to tell me which rules we are following to write electronic configuration here. Yeah, try to recall those concepts. So what are the rules which we follow to fill electrons in atomic orbitals? Children, quickly answer. Yes, you people are correct. The one is Aufbau principle. Right now, this is first Aufbau principle. What does this principle says? Yes, remember no? That electrons are always filled in increasing order of energy. Orbital with low energy filled first, followed by increasing order. Second rule, what was that? Pauli's exclusion principle. This was the second one. And this principle says that in an orbital, maximum 2 electrons are present with opposite spin. Right? Third one was Hund's rule. Hund's rule of maximum multiplicity. This rule tells how electrons are filled in degenerate orbitals. Like in P, there are 3. In D, there are 5. In F, there are 7. So this principle says that electrons, they are filled one by one. Means pairing doesn't take place until each one is singly occupied. Like in case of P, P1, P2, P3. Pairing starts with P4. Clear now? These three rules were there. Same rules we will be using while filling electrons in molecular orbitals. Absolutely same rules, no difference at all. Now, just discuss how do we use these principles here. In case of molecular orbital, the first molecular orbital would be which one? We discussed right now here. Yes, it is sigma 1s. And then the next one is sigma 2s. No, no. It is sigma 1s anti-bonding. Because we get bonding and then we get anti-bonding. Yes. So the first one is sigma 1s. The higher energy orbital. The next one is sigma star 1s. Similarly, we will be having 2s bonding and then 2s anti-bonding. So this is sigma 2s and then sigma star 2s. Yes children, after 2s, which orbital is the next one? Correct. It is 2p. So the next one is, but in p, I think now you remember pi 2px, then pi 2py, and then sigma 2pz. So this is pi 2px equals to pi 2py. These two are degenerate because both are forming pi bonds. And then we will be having sigma 2pz. This is the bonding level. Now, next would be the anti-bonding level. So this is pi star 2px equals to pi star 2py, and then the next and the last one is sigma star 2pz. Clear children? I think this is very simple. But here note down one very important aspect, that this order of electronic configuration, this is applicable for those molecules where number of electrons is either equal to or less than 14. Clear? The systems having number of electrons equal to or less than 14. In all these cases, we will be following this order of writing electronic configuration. Clear? No problem? Okay. Just discuss this thing in detail by taking few examples so that we can easily apply this concept now. Begin with the simplest case of hydrogen molecule. Hydrogen molecule is formed by two atomic hydrogen atoms. So simple. And atomic number of hydrogen is 1. So in case of H2, total number of electrons are 2 electrons. Means we need to fill 2 electrons here. How? Absolutely simple. This is clear here. First, electrons, they will go to sigma 1s. Which principle we are using here? Of principle, right now? Now these 2 electrons, we give 1 to sigma 1s and 1 to sigma star 1s, or the second option, we can give both electrons here, which is correct. Again, Aufbau principle is going to tell us that which one is correct. Aufbau principle says first electrons enters into lower energy level. That is 1s has less energy as compared to sigma star 1s. So of course first 2 electrons will go to sigma 1s. Then electrons will enter into sigma star 1s, that is anti-bonding. But as no electron is left, it means it remains vacant, no electron. Clear, children? Now this electronic configuration seem to be so simple, but actually this is very important for us. It's going to help us to solve so many problems. How? It can tell us the magnetic behavior of particular case. How can we explain magnetic properties by using this electronic configuration? Broadly, there are two types of species on the basis of magnetic properties: paramagnetic and diamagnetic. Now, how to judge which one is para and which one is dia? If unpaired electrons are present, this is paramagnetic. Pair electrons, this is diamagnetic. Paramagnetic are the species which are weakly attracted by external magnetic field. Dia, they are repelled, weakly repelled by external magnetic field. So, both things clear? Now, children, apply this concept here and try to tell me H2 is a diamagnetic or paramagnetic. Suppose, just for example, if I'm saying hydrogen is a paramagnetic molecule, what will you say? Check here and please tell me. Yes, you people will definitely say, ma'am, you are wrong. Because here paired electrons are present. And if paired electrons are present, how it can be? How it can be? Paramagnetic. Cannot. No. Paired electrons means diamagnetic. No one can confuse you. If you know this concept, easily you can tell here that as it has paired electron, no unpaired electron is there, means this molecule is a diamagnetic molecule. Clear? This is the first thing from electronic configuration. We can tell their magnetic nature. Second thing, we can compare the relative stability of different species, or we can tell about the existence of a species, whether the particular case exists or not. How? By knowing the bond order. For this, we need to calculate bond order. Formula to calculate bond order is half of the difference of bonding and anti-bonding electrons. Half of the difference of bonding and anti-bonding electrons. Nb is number of bonding electrons. Na number of anti-bonding electrons. Again, we discuss case of hydrogen molecule. How many bonding electrons it has? 2. Clear? How many anti-bonding? 0. So, the bond order 2 minus 0 divided by 2, answer would be 1. From this 1, we can say that there is a single bond between hydrogen and hydrogen. It can give the information of bonds also. 1 means a single bond is present. If bond order comes 0, molecule does not exist. So easy to tell now whether existence is there or not. 0 bond order, molecule will not exist. More than 0, it will exist. And stability is directly proportional to bond order. How stability is related to bond order? Directly proportional. Higher is the bond order, more would be the stability. So in this way, easily you can compare different cases if asked that which one is more stable. The one with higher bond order, of course, is more stable. So easy? Clear now? Next thing, we can also compare the bond lengths. Bond length is inversely proportional to bond order. Bond length is inversely proportional to bond order because we know that smaller is the bond, more would be the stability. And more stability means high bond order. So we can easily say that bond length and bond order are inversely proportional. Yes, my dear children. Clear all these things? If I ask few questions based on this, will you be able to answer me? I have full faith on you that you can easily answer me. Okay, just take a case. Suppose I'm giving to you that compare the stability of hydrogen molecule, its cation and its anion. That what is the stability order? So how do we go? First, we should write their electronic configuration. From electronic configuration, we can find their bond order. And after getting bond order, it's very simple to tell which is more stable. Yes? So, okay, write the electronic configuration for cation. It's cation. All of you know well that cations are formed by loss of electrons. As it is monovalent cation, means one electron is already released. H2 has 2 electrons. One is given, means how many are left with us? Only 1 electron. So we will be writing electronic configuration for this 1 electron, that is sigma 1 is 1. Correct? And if we take its anion, anions are formed by gain of electrons. So H2 has 2 electrons and after receiving 1 more, total becomes 3 electrons. So now write electronic configuration for 3 electrons, that is sigma 1 is 2 and the third electron will goes to sigma star 1 is 1. Now we check their bond orders. Bond order, half of the difference of bonding and anti-bonding electron. So children, please tell me, how many bonding electrons here? 1. How many anti-bonding? 0. So 1 minus 0 divided by 2, the answer is 0.5. Yes? Same here, if we use it. How many bonding electrons? 2. How many anti-bonding electrons? 1. So bond order, 2 minus 1 divided by 2, again it's 0.5. One thing which we talked in VBT, that here bond orders can come in fractions. This was missing in VBT, but here MOT explains this thing. So this is the beauty of MOT, that here we talk about fractional bond orders even, which we couldn't discuss in VBT. Now, relative stability of these three. As I told you, higher is bond order, more is stability. So the highest bond order is in case of H2. This is 1. In these two cases, this is coming 0.5. So one thing is clear to us, that H2 is most stable. But there is a confusion between these two. You must be thinking that, ma'am, as their bond orders are same, so of course they will be having same stability. But no, this is the twist here. If you remember the basics of MOT, you can easily tell that anti-bonding orbitals, they are higher in energy. It means low in stability. So the species having more anti-bonding electrons would be having more energy, means less stable. So whenever bond order comes equal, just compare their anti-bonding electrons. The one with more anti-bonding electrons is of course less stable. So just check in its cation, we don't have any anti-bonding electron. This is going to increase its stability. But in its anion, we have one anti-bonding electron. So now we can easily say that cation is more stable as compared to anion. So this is the stability order which we can easily compare. Then we can tell their magnetism. H2, it was diamagnetic as non-paired electron was there. Here we will be having one unpaired electron. So it is paramagnetic. Same one unpaired electron in anion. So both its cations and anions, they are paramagnetic due to the presence of unpaired electrons. So there are so many things which we can easily answer if we know how to write electronic configuration for molecular orbital. Yes, my dear children, now I think this concept is clear to you to some extent, I would say, because still we haven't discussed many examples, but at least one example is clear to us. Now, I'm giving you next example, helium molecule. Right? Just try this. Atomic number of helium 2. So, helium molecule, how many electrons? 4 electrons are there. Just start writing electronic configuration. First 2 electrons will enter into sigma 1s of Bohr principle. Maximum 2 electrons we can give. Which principle is this? Pauli's exclusion principle. In an orbital, maximum 2 electrons we can give. So these 2 electrons we have given to sigma 1s. Now next 2 electrons will enter into sigma star 1s2. I think here you must be confused to some extent. That ma'am, helium is a noble gas, how it is making a molecule. So dear, the existence of helium, whether it's going to exist or not, we will be telling by using MOT. MOT will answer us that whether this will exist or not. So now we write its bond order. Bond order. Number of bonding electrons minus anti-bonding electrons divided by 2. How many bonded electrons? 2. Anti-bonding also 2. So its bond order 2 minus 2 divided by 2. Answer comes 0. 0 means this molecule does not exist. So easy to tell now that which case is going to exist and which one is not. No confusion, I think so. Let us take one more example. Then I will give you few cases to try. Nitrogen molecule. How many electrons total? Atomic number of nitrogen 7. So its molecule, this has 14 electrons. Start writing, filling of these 14. First of all, sigma 1 is 2, sigma star 1 is 2, sigma 2 is 2, sigma star 2 is 2. Quite boring, na? That again and again we are writing the same things, repeating the same things again and again. No problem. I will give you a shortcut. But first, let us complete this. How many electrons? 2, 4, 6, 8. Right? Then after sigma 2 is 2, this is 1s, this is 2s. We will be having 2p. Pi 2px equals to pi 2p y. First electron here, second here, third here, fourth again here. Right? Order how we will be filling as these are degenerate. So, Hans rule we apply here. That first electron will go here. Second in this case. Third will come here. Fourth will go pi. So, total 8 electrons. 9, 10, 11, 12. So, 2, 2. 2 are left. These 2 electrons will enter into sigma 2pz. Understood? Now again coming to this part. That why again and again we have to write 1s, 2s in this way. To simplify this, as these are completely filled inner cores. So for 1s we may write kk. And for 2s kk dash. That's it. So simple. Again, we don't have to write again and again all these things. And how many electrons are covered here? 8 electrons. So straightway 2, 4, 6, 8. Straightway we will start with 9th electron here. So in all further cases, in where large number of electrons are present, at the place of these two inner cores, you may write Kk and Kk dash. It's clear 8 electrons are completed up to here. And then we can easily skip this part for calculation of bond order also. Why? Because bond order is the difference of bonding and anti-bonding electrons divided by 2. Two bonding, two anti-bonding. Cancel out each other. Doesn't make any difference in the result. Same here. Two bonding, two anti-bonding. Again cancel out each other. Result remains unaffected. That's why while calculating bond order, here no need to consider these inner cores. Simply we can answer on the basis of outer core. Look here, how can we do? Bond order, number of bonding. I'm skipping this thing. Got it? Bonding electrons 2, 4, 6. Minus anti-bonding, no, 0 divided by 2. Answer is 3. What does it signify? Is 3. Means a triple bond is present between nitrogen and nitrogen. Correct, na? As well as we can tell the magnetic property. Children, try to answer me. Para or dia? Please tell. Yes, diamagnetic. Because no unpaired electron is there. All are paired. Paired means diamagnetic. Correct? Now I think you can easily answer few more cases if I give you to try. So note down. Just compare the relative stability of nitrogen, its cation and its anion. You need to try these cases. Also, you need to tell the magnetic behavior of these materials. So, again, this part we have covered. This part means where number of electrons equal to 14 or less than 14. Another case we will be discussing where number of electrons would be number of electrons 15 to 20. If the number of electrons are from 15 to 20, almost same electronic configuration will be followed. Don't worry, no major changes there. But yes, one change, only this part. That's it. Beginning is same Kk dash, no change. Ending is also absolutely same. Here the change is again very simple. This simply you have to reverse this order. Sigma to Pz followed by pi to Px equals to pi to P. Clear? Just discuss one case to make it clear to you people. Oxygen, a very important case. Many times examiners ask questions on this one. O2 molecule. First total number of electrons, 16 electrons, right? Shall I write 1s2, 2s2 or in this way? No. Now we may write Kk and Kk dash. How many electrons are covered here? Total 8 electrons. Remember? Yes. Now, ninth electron will enter into sigma to Pz. 10th also will go here because maximum 2 electrons. Sigma to Pz. 2 electrons. 8 plus 2, 10. 11, 12, 13, 14. So then, pi to Px2 equals to pi to Py2. How many are there? 8. 10, 12, 14. 2 more electrons are there. Where will they be? Coming to this level, pi star to Px equals to pi star to Py. Now there is a query. Shall I give both the electrons to Px? Or I should distribute one into Px and one into Py? Quite confusing. Which rule is going to help me here? Yes, you people are right. It's Hund's rule of maximum multiplicity. We discussed now. This rule says in degenerate orbitals, the filling of electron takes place one by one. Means we cannot pair up until each one will get single electron. So first electron to pi to px, second to pi to p pi. Got it? Now we find its bond order. Bond order, bonding minus anti-bonding. No need to take inner core. Simply we can answer on the basis of outer core. How many bonding electrons? 2, 4, 6. So it is 6 minus. How many anti-bonding? 1, 2. Divided by 2. So it is 4 by 2, that is 2. Bond order 2 means oxygen, oxygen, double bond is present. Now let us discuss its magnetic behavior. Unpaired electrons are there, means paramagnetic. Remember, VBT says oxygen is a diamagnetic molecule, but here it's clear why oxygen is not diamagnetic. This is a paramagnetic molecule. This was the major drawback of VBT, because according to VBT, it was not possible to explain why oxygen is paramagnetic. Here we can easily tell this. Clear? Now again there's a question for you. Compare the stability of O2, its cation, its monovalent anion, its divalent anion. Just try their relative stabilities on the basis of the electronic configuration, bond order. You can easily tell which one is more stable and why. Then after comparing their relative stability, try to answer their magnetic nature also. I'm sure you can easily do all these things. Yes, children, now I think so that all these concepts are absolutely clear to you. After this, the last topic of MOT is energy level diagram. Energy level diagram. MOT is a quite long theory. So by now you must be thinking that ma'am, हमारा energy level बहुत नीचे चला गया. Now we are feeling so low in energy. No problem, just pause the video. Go and take any good energy drink, come back and again start. But for me it's okay, I can continue. So how to draw energy level diagrams? If this concept of increasing order of energy is clear to you, you can easily draw the energy level diagram. Simply in this case, we have to show the orbitals, that's it. We will be following the same level without any change. Like first of all, which molecular orbital comes? Sigma 1s, sigma star 1s. How they are formed? Remember the previous concept. By constructive and destructive interference of 1s with 1s. So we need to take two 1s atomic orbitals. This is 1s, this is another 1s. These two are the atomic orbitals. When these two atomic orbitals, they show constructive and destructive interference, we will be getting two molecular orbitals. One is bonding and the second is anti-bonding. So just make two levels, one for bonding orbital, second level for anti-bonding orbital. This is bonding, this is anti-bonding. Sigma 1s, sigma star 1s. Simple. After 1s, the next orbital will be 2s. So here this is 2s, this is also 2s. Again represent two levels, bonding and anti-bonding. This is sigma 2s, this is sigma star 2s. This one is the increasing order of energy. After 2s, the next orbital come will be 2p. You will be drawing it here. In this way, you will be moving. But as I don't have any space here, I don't want to clear this space because we need this increasing order. That's why I will be showing 2p here. But again I am repeating, 2p will come at this level. 1 is, 2 is, 2p. Clear? So just start here with 2p. In case of 2p, we will be having 3 levels. That is 2px, 2py and 2pz. Same for second item. 3D generate 2px, 2py, 2pz. So with p orbital, when these 6 orbitals shows constructive and destructive interference, we will be getting 6 molecular orbitals, 3 bonding, 3 anti-bonding. But again, one thing. In bonding also we will be having 2 levels. Same energy, sigma 2pz, higher energy. So bonding we will be making 2 levels. Anti-bonding also we will be making 2 levels. So this is first 2 levels for bonding and then 2 levels for anti-bonding. Pi 2px equals to pi 2py, low energy. Pi 2px, pi 2py. Higher energy one is for sigma 2pz. Sigma. Now show 2 levels for anti-bonding. First pi star 2px, then pi star 2py. Pi star 2px, pi star 2py. And the last one is sigma star 2pz. This is the simplest way to draw energy level diagrams. Now filling of electrons in the same way as we have already written in case of electronic configurations. Let us discuss the case of nitrogen molecule again. Electronic configuration for atomic nitrogen. 7 atomic number, 1 is 2, 2 is 2, 2px1, 2py1 and 2pz1. Similarly, we will be writing here. Understood? First, 1 is 2. These are the 2 electrons. These 4 electrons we will be filling in molecular orbitals, 2 in each. Same now, this we have already written in electronic configuration. Now the next, 2 is 2. 2 electrons in 2 is 2 here. 2 in molecular orbitals now seem to be quite simple. Come here, 1 to each. 6 electrons, 2, 4, 6. Complete. This energy level diagram we will be showing for elements having total electrons up to 14. More than 14, there one difference was there. Remember, this was the difference now here at this part. What you need to do? Simply reverse this case. Sigma 2pz will come here, pi 2px and pi 2py will go at this place. Clear? So, this was all things about molecular orbital. Nothing is left. All concepts are clear. We discussed in detail about their magnetic properties, electronic configuration, bond order, this, that, everything. So, try to revise all these things. Try to solve all the questions so that you can easily answer any question based on MOT.